We live in an age where distance feels defeated. Messages cross oceans instantly, images travel around the planet in seconds, and a device in our hands can show us any place on Earth as if geography itself has surrendered. This constant immediacy quietly reshapes the way we think about the universe. When someone says Pluto is part of our solar system, it feels close, almost familiar. When astronomers say Proxima Centauri is the nearest star, our minds instinctively translate that into something reachable, something waiting just beyond the edge of our grasp. But space does not operate on human intuition. It is not a larger version of Earth, not an extension of our roads and routes. Space is a fundamentally different environment, governed by scales of distance and time that resist emotion, ambition, and imagination alike. Pluto is a perfect example of this illusion. On diagrams it appears as a small dot at the edge of a neat planetary lineup, but in reality it exists in a region where sunlight is weak, heat is scarce, and distance becomes oppressive. To reach Pluto, NASA launched New Horizons on one of the fastest trajectories ever achieved by a spacecraft. Even then, the journey took nearly a decade. And when the probe finally arrived, it did not slow down and settle into orbit. It rushed past, collecting data during a brief encounter before disappearing into the darkness beyond. Slowing down would have required carrying far more fuel, which would have demanded a heavier spacecraft, which in turn would have required an even more powerful launch. In space, every solution multiplies the problem. Distance is not just something you cross. It is something that extracts a cost at every stage. This is the first hard lesson space teaches humanity. The farther you go, the less you can bring with you. Every kilogram of fuel demands more fuel to carry it. Every instrument adds weight. Every layer of protection increases mass. At some point, ambition collapses under its own requirements. Pluto is not a destination in the way cities are destinations. It is a boundary, a place where exploration becomes a fleeting glance rather than an arrival. Even within our own solar system, distance already forces compromise. And yet Pluto is still home territory compared to what lies beyond. Proxima Centauri, the nearest star outside our solar system, exists in an entirely different category of distance. At 4.24 light-years away, it is close by stellar standards, but that closeness is deceptive. A light-year is not a convenient astronomical label. It is the distance light itself travels in 1 year, moving at nearly 300,000 kilometers per second. When translated into human terms, 4.24 light-years becomes a number so vast it stops functioning intuitively. It is not a journey measured in days, months, or even decades, but in spans of time that exceed civilizations. This is what makes Proxima Centauri so haunting. It is not hidden in the far reaches of the galaxy. It is right next door, close enough to provoke longing, close enough to feel like the first step into the stars. And yet it remains unreachable with any technology we possess today. Even the fastest spacecraft humanity has ever built would need tens of thousands of years to arrive. That fact alone reframes what it means to be a spacefaring species. If we cannot reach the nearest star, then the universe we so confidently map and study is, in a very real sense, still closed to us. Modern astronomy deepens this paradox. Our telescopes have become extraordinarily powerful. We can detect planets orbiting distant stars by measuring the slightest changes in starlight. We can analyze atmospheres across light-years of space. We can infer temperatures, compositions, and even weather patterns on worlds we will never see directly. In some cases, we can identify planets that resemble Earth in size and position, worlds that orbit in regions where liquid water might exist. Knowledge flows freely toward us, carried by ancient photons that left their stars long before human civilization began. But knowledge does not shorten distance. Telescopes expand awareness, not reach. They allow us to see without touching, to understand without arriving. This creates a uniquely modern frustration. We can point to planets by name, discuss their climates, and speculate about life, yet remain physically locked inside a small bubble of space around our sun. The universe has become familiar without becoming accessible. This gap between observation and presence is one of the defining tensions of our era. Humanity has never known so much about places it cannot visit. In earlier centuries, unknown lands were unknown because they were unseen. Today, unknown lands are mapped, catalogued, and studied, yet still forbidden by distance and physics. The universe invites our curiosity while denying our body's entry. The psychological impact of this cannot be ignored. Humans evolved to measure distance in terms of effort and survival. A long journey on Earth is exhausting, but it remains human in scale. It happens within a lifetime. Interstellar distance breaks that relationship. It transforms travel into something abstract, something detached from individual experience. A mission to another star is not a journey one person undertakes. It is a commitment made by a civilization to an outcome it will never personally witness. This raises questions that go far beyond engineering. Even if propulsion were solved, even if energy were abundant, could a society maintain purpose across centuries or millennia? Could generations remain committed to a goal none of them would reach? Space travel at this scale demands not only technology, but cultural continuity, political stability, and shared meaning across time. History offers little reassurance that such continuity can be maintained. And yet Proxima Centauri exerts an almost gravitational pull on the human imagination, amplified by the discovery of Proxima Centauri b, a rocky planet orbiting within its star's habitable zone. The phrase itself, habitable zone, is dangerously seductive. It suggests oceans, skies, and the possibility of life. It makes the planet feel less like data and more like a place. A destination. But the term is misleading. A habitable zone only describes temperature, not safety. It says nothing about radiation, atmospheric stability, or long-term survival. Red dwarf stars like Proxima are volatile, prone to violent flares that can strip planets of their atmospheres and sterilize their surfaces. A planet can sit in the right place and still be utterly hostile. Still, proximity combined with possibility creates longing. Proxima b becomes a symbol of what might exist just beyond our reach, a reminder of both our potential and our limitations. It represents the first door beyond the solar system, a door we can see clearly but cannot open. This is the deeper truth beneath the question of why we cannot reach Pluto or Proxima Centauri. The barrier is not a lack of intelligence or desire. It is the collision between human scale and cosmic scale. We are creatures shaped by lifetimes, by days and years, attempting to navigate a universe measured in light years and eons. Our tools grow more powerful, our models more precise, but the fundamental mismatch remains. The frontier we imagine, filled with reachable stars and inhabited worlds, may not be blocked by fear or imagination at all. It may be constrained by the very structure of reality. Physics does not negotiate. Distance does not care about ambition. Time does not bend to longing. And yet this does not make the story meaningless. On the contrary, it makes it essential. Because the question is no longer simply how far we can go, but what it means to try. Pluto and Proxima Centauri are not just locations in space. They are mirrors, reflecting the limits of our technology, our biology, and our patience. They force us to confront the uncomfortable possibility that exploration, at its greatest scale, may demand sacrifices not of fuel or metal, but of certainty, immediacy, and even personal relevance. The universe allows us to look outward with extraordinary clarity, while reminding us that reaching outward is an entirely different challenge. And it is within that tension, between vision and limitation, that the true story of space exploration begins. The moment humanity tries to move faster in space, reality pushes back. On Earth, speed feels like a matter of better engines and more power. Faster cars, faster planes, faster computers. Progress has trained us to believe that velocity is a problem waiting to be solved. In space, speed is something far more unforgiving. Every increase in velocity demands an exponential increase in energy, and that energy must be carried from the moment of launch. Unlike an airplane, a spacecraft cannot refuel easily, cannot rely on air to lift it, and cannot discard the burden of gravity without paying a cost. In space travel, fuel is not just a resource. It is a chain that binds ambition to mathematics. Rockets operate on a simple principle: to move forward, you must throw mass backward. That mass is fuel, expelled at high speed to push the spacecraft in the opposite direction. This works, but it creates a brutal loop. The more fuel you need, the heavier the spacecraft becomes. The heavier the spacecraft becomes, the more fuel you need to move it. At interplanetary distances this is manageable, though expensive. At interstellar distances it becomes overwhelming. Each additional kilogram of payload demands several kilograms of fuel, which themselves demand even more fuel to lift them off Earth. Very quickly, the numbers explode beyond practicality. This is why most of a rocket's mass at launch is fuel. The engines, the instruments, the scientific payload, and any protective shielding make up only a small fraction of the total weight. The rest exists solely to escape Earth's gravity and accelerate the spacecraft to a meaningful speed. Once that fuel is burned, the spacecraft is committed. There are no second chances, no easy course corrections, no opportunity to slow down unless additional fuel was carried from the start. Space does not forgive inefficiency. This constraint defines everything about deep space travel. To reach Pluto, New Horizons had to be launched on a trajectory that stole momentum from planetary flybys, using gravity itself as a tool. Even then, its speed was modest by cosmic standards. To reach another star, even that would not be enough. The velocities required are not a little faster, but orders of magnitude faster. And this is where the tyranny of fuel becomes absolute. As a spacecraft accelerates, it does not simply move faster through space. It carries more kinetic energy, and energy must come from somewhere. Chemical rockets, the kind we use today, are limited by the energy stored in chemical bonds. No matter how refined the design, there is a ceiling to how much thrust they can provide. Nuclear propulsion can offer improvements, but not miracles. Even the most optimistic nuclear concepts fall far short of what would be required for practical interstellar travel within human timescales. At a certain point, engineers encounter a wall not of technology, but of physics. The energy needed to push a macroscopic object to a significant fraction of the speed of light is immense. At 10% of light speed, the kinetic energy involved is already staggering. At 20%, it becomes civilization scale. To accelerate even a small spacecraft to such velocities would require an energy output comparable to years, or even centuries, of total planetary power production. This is not a technical inconvenience. It is a fundamental imbalance between desire and capacity. This is why the phrase "just go faster" is misleading. Faster means heavier. Heavier means more fuel. More fuel means more energy. More energy means greater risk. At interstellar scales, speed becomes a liability as much as an asset. The universe does not reward haste. The tyranny of fuel is not merely a technical issue. It is a philosophical one. It forces humanity to confront the possibility that certain dreams cannot be achieved by incremental improvement alone. That there may be thresholds beyond which progress does not continue smoothly, but stalls entirely unless something fundamentally new is discovered. And so the nearest star remains distant not because we lack the will to reach it, but because every path toward it demands a price we are not yet capable of paying. The challenge is not finding a faster engine. It is finding a way to escape a cycle where every gain demands an even greater sacrifice. Even if humanity could solve the problem of propulsion, even if engines could push a spacecraft to extraordinary speeds without collapsing under their own fuel requirements, space itself would still remain an active and hostile environment. The common image of space as a silent, empty void is deeply misleading. Interstellar space is not peaceful emptiness. It is a sparse but relentless battlefield where energy, particles, and radiation move without mercy. At low speeds and short distances, these dangers are manageable. At interstellar scales, they become existential threats. Cosmic radiation is the first of these invisible enemies. It comes from everywhere at once: high-energy particles launched by supernovae, black holes, and violent stellar events across the galaxy. Unlike radiation near Earth, which is softened by our planet's magnetic field and atmosphere, interstellar radiation strikes unfiltered. Over time, it damages electronics, corrupts data, and shatters the molecular structure of materials. For biological life, it is even more unforgiving. DNA breaks down under sustained radiation exposure, increasing mutation rates and eventually making survival impossible. No spacecraft material currently known can fully block this radiation without adding prohibitive mass, and even partial shielding degrades over long timescales. Then there is interstellar dust. Each cubic meter of space contains microscopic grains of matter, remnants of ancient stars and planetary systems. Individually, they are harmless. At extreme velocities, they become catastrophic. When a spacecraft traveling at a significant fraction of light speed collides with a dust particle smaller than a grain of sand, the energy released rivals that of an explosive device. At those speeds, there is no gradual erosion. There is sudden destruction. Shields thick enough to withstand such impacts would be impossibly heavy, and active defense systems would require reaction times faster than physics allows. The faster the spacecraft travels, the more lethal the environment becomes. These dangers scale with time as well as speed. A journey to another star is not a brief exposure, but a prolonged assault lasting decades, centuries, or even millennia. Every system aboard the spacecraft must survive without maintenance, without replacement parts, and without human intervention. On Earth, machines are designed for lifetimes measured in years or decades. Even our most durable satellites eventually fail. Expecting a complex system to function flawlessly for hundreds or thousands of years stretches credibility beyond reason. Communication introduces another brutal limitation. Signals travel at the speed of light, which means that any message sent from an interstellar probe takes years to reach Earth. A command sent today would arrive long after circumstances had changed. Real-time control becomes impossible. The spacecraft must be autonomous, capable of making decisions without guidance, adapting to unforeseen conditions with no help from home. Artificial intelligence may offer partial solutions, but autonomy at this level introduces its own risks. A small error, uncorrected for centuries, can doom an entire mission. Navigation itself becomes uncertain across interstellar distances. Stars move. Their positions shift over time. A deviation so small it would be meaningless within the solar system can grow into a miss measured in billions of kilometers over light-year distances. To aim accurately, humanity would need not only precise knowledge of where a star is now, but where it will be decades or centuries in the future. And even perfect calculations cannot account for every gravitational influence or random interaction along the way. This is why interstellar travel is not simply an extension of interplanetary travel. It is a different category of challenge altogether. Within the solar system, mistakes are survivable. Missions can be corrected, redirected, or abandoned with limited loss. Between the stars, error is final. There are no rescue missions. There is no second attempt. A spacecraft that fails halfway to Proxima Centauri does not drift back. It becomes debris, frozen in motion, carrying the ghost of a failed ambition forever. All of this exposes a deeper paradox. The universe allows us to observe it with stunning clarity, yet punishes us severely for attempting to move within it at scale. Distance magnifies every weakness. Time amplifies every flaw. The systems that function beautifully for years crumble when asked to endure centuries. The materials that perform reliably in Earth orbit degrade when exposed to interstellar radiation. The strategies that work within planetary neighborhoods collapse in the vastness between stars. And yet, despite these realities, humanity continues to imagine reaching Proxima Centauri. Not because it is easy, but because it is close enough to feel personal. It represents the first test of whether we are confined to our cosmic island or capable of becoming something more enduring. The obstacles are not merely technical. They challenge our assumptions about progress itself. We are used to thinking that knowledge accumulates, that solutions build upon one another, that each generation stands taller than the last. Interstellar space does not reward that model. It demands patience measured in eras, not careers. At this scale, the question changes. It is no longer about how to build a ship. It becomes a question of whether a civilization can remain coherent across the span required to complete the journey. Whether meaning can survive without a rival. Whether purpose can be sustained when success is defined by someone else, far in the future, receiving the result. And even if all of this were overcome, even if propulsion, shielding, navigation, and autonomy were solved, another barrier still waits ahead. A barrier not of physics or engineering, but of biology, psychology, and time itself. Because the hardest part of reaching the stars may not be surviving space, but surviving ourselves. Even if technology could overcome radiation, dust, and navigation, the journey to another star would still collide with a far more intimate limitation: time as experienced by the human species. Interstellar travel is not merely a test of machines, but a test of biology, psychology, and culture. A voyage lasting centuries or millennia transforms travel into inheritance. Those who begin the journey will never see its end. Those who arrive will never know Earth. This alone reshapes the meaning of exploration. For all of human history, exploration has been driven by the promise that the explorer would witness discovery. Interstellar travel breaks that promise completely. It demands faith across generations, loyalty to a mission whose reward belongs to strangers not yet born. The concept of generation ships emerged as a way to confront this reality. Instead of racing toward the stars, a civilization might build a self-contained world in motion, a vessel large enough to support human life for centuries. Children would be born, grow old, and die aboard the ship, never knowing another sky. Entire societies would exist solely to maintain a trajectory set long before their birth. In theory, such a ship solves the problem of time. In practice, it opens problems far more complex than propulsion. Maintaining genetic diversity, preventing social collapse, preserving knowledge, and sustaining purpose over dozens of generations has no historical precedent. Human societies struggle to remain stable over decades, let alone centuries, even under familiar conditions. A sealed environment drifting through hostile space magnifies every weakness. Psychology becomes a critical factor. Humans are not designed for infinite confinement. Even on Earth, isolation experiments reveal how quickly mental health deteriorates without open environments, novelty, and perceived freedom. A generation ship offers none of these. Every horizon is artificial. Every environment is engineered. The knowledge that there is no escape, no alternative destination, no turning back, weighs heavily on the mind. Over time, belief systems would inevitably change. The mission's original purpose could erode, replaced by new priorities shaped by life aboard the ship rather than the destination it was meant to reach. Eventually, descendants might question why the journey should continue at all. Culture itself becomes fragile under these conditions. Language evolves. Traditions shift. Knowledge must be actively preserved to survive. Even on Earth, vast amounts of information are lost within a few generations if not deliberately protected. On a generation ship, failure to transmit critical skills or understanding could be fatal. A single breakdown in education, governance, or social cohesion could doom the entire mission long before it reaches another star. Unlike Earth, there is no margin for collapse. There are no external resources, no rescue, no reset. Cryogenic preservation is often proposed as an alternative, allowing travelers to sleep through the centuries. But this solution remains speculative. Long-term preservation of complex biological systems without damage has never been achieved. Even if it were possible, the psychological consequences of awakening into a completely alien time are unknown. The world left behind would no longer exist. Language, culture, and history would have moved on. The traveler would arrive not as an explorer, but as a relic displaced in time. Time dilation, predicted by relativity, offers little comfort. While extreme velocities can slow time for travelers relative to those left behind, reaching speeds where this effect becomes meaningful requires energy far beyond our reach. For humanity as it exists today, time remains an uncompromising barrier. Every interstellar dream must be paid for not just in energy, but in lifetimes. This forces an uncomfortable question. Is humanity willing to invest its future in projects whose success it will never personally witness? Modern civilization is built around short feedback loops: elections, economic cycles, technological upgrades. Interstellar travel demands the opposite. It demands patience beyond instinct, sacrifice without reward, and trust across centuries. It asks whether our species can think not just beyond borders, but beyond generations. In confronting this question, space exploration stops being about stars and planets. It becomes a mirror held up to humanity itself. Our technologies reveal what is physically possible. Our willingness to endure reveals who we are. And as the distance to the stars stretches endlessly ahead, It becomes clear that the greatest barrier may not lie in space at all, but in whether human civilization can remain coherent long enough to cross it. Even if humanity could somehow endure the centuries required for interstellar travel, even if societies remained stable and technology survived intact, another uncomfortable reality waits at the destination itself. Reaching another star does not guarantee finding a welcoming world. Distance hides danger as effectively as it hides beauty, and the closer scientists look at so-called Earth-like planets, the more complex and fragile the idea of habitability becomes. A planet can resemble Earth in size and orbit, yet still be utterly hostile to life as we know it. Proxima Centauri b is a perfect example of this contradiction. On paper, it looks promising. It is roughly Earth-sized and orbits within the region where liquid water could exist. But Proxima Centauri is a red dwarf star, and red dwarfs behave very differently from our Sun. They are smaller and cooler, but also far more violent. They produce frequent and powerful stellar flares that flood nearby planets with intense ultraviolet and X-ray radiation. For a planet orbiting so close, these flares are not occasional events. They are a constant assault. Over geological time, such radiation can strip away an atmosphere entirely, erasing oceans and rendering the surface sterile. This challenges one of the most comforting assumptions in astronomy, that finding a planet in the right place is enough. Temperature alone does not create habitability. A stable magnetic field, atmospheric retention, chemical balance, and long-term stellar stability all matter just as much. Remove any one of these, and a world that appears ideal becomes unlivable. The universe does not reward simple checklists. It produces environments shaped by countless interacting variables, many of which work against life rather than for it. Observations from modern space telescopes have made this clearer than ever. Some planets that should be temperate appear far hotter than expected. Others that should be dry show signs of water vapor. Worlds once imagined as static turn out to be dynamic, unstable, and often extreme. This unpredictability suggests that life-friendly conditions may be rarer than early optimism implied. The galaxy may be filled with planets, yet sparsely populated with places where life can persist for billions of years. Even if a planet retains an atmosphere, survival is not guaranteed. Many exoplanets are tidally locked, with one side permanently facing their star and the other locked in eternal night. This creates extremes of temperature and climate that challenge atmospheric circulation and long-term stability. On such worlds, habitability may exist only in narrow regions, fragile and easily disrupted. A single change in stellar output could tip the balance irreversibly. This reality reshapes the purpose of interstellar travel. The dream is often framed as escape, as if humanity could simply move on once Earth becomes inconvenient or damaged. But the universe does not offer replacements easily. Earth is not merely habitable, it is extraordinarily stable. It has a magnetic field strong enough to shield life, a large moon that stabilizes its rotation, plate tectonics that recycle carbon, and a star that has remained remarkably calm for billions of years. These are not common traits. They are coincidences layered upon coincidences. Seen this way, the search for other worlds becomes less about finding a new home and more about understanding how rare our current one might be. Each hostile exoplanet is a reminder that survival is not the default outcome of planetary formation. Life, at least complex life, appears to require a narrow corridor of conditions maintained over immense spans of time. Interstellar travel may reveal many wonders, but it may also reveal that Earth is unusually forgiving. This realization introduces a philosophical shift. If suitable destinations are rare and dangerous, then the motivation for reaching them changes. Exploration becomes less about colonization and more about knowledge. Probes may arrive where humans cannot. Data may return even if people never do. The goal shifts from expansion to understanding, from settlement to perspective. And this brings humanity back to a humbling truth. We are not trapped on Earth by lack of imagination. We are anchored here by an extraordinary alignment of conditions that may not be easily replicated elsewhere. The stars beckon, but they do not promise safety. They offer challenge, uncertainty, and perspective. As telescopes continue to peer deeper into the galaxy, the universe reveals itself not as a welcoming frontier waiting to be claimed, but as a complex and often hostile environment where survival is exceptional, not guaranteed. And in recognizing this, the dream of reaching another star begins to change shape. It becomes less about escape and more about responsibility. Because before humanity can hope to live elsewhere, it must understand why it was able to live here at all. As the search for distant worlds grows more precise, a quieter realization begins to surface. The greatest obstacle to reaching the stars may not be distance, radiation, or fuel, but the way humans perceive time itself. Interstellar space operates on scales that are fundamentally incompatible with human life as it is currently lived and understood. Our biology, our psychology, and even our sense of meaning are built around short horizons. We think in days, years, and lifetimes. The universe moves in epochs. When those two rhythms collide, ambition fractures. Every major human achievement has relied on a feedback loop. Effort leads to reward. Sacrifice produces visible outcome. Explorers returned home. Builders saw their structures rise. Scientists witnessed the results of their experiments. Interstellar travel breaks that loop entirely. A mission launched today toward another star would unfold across centuries. The people who design it, fund it, and initiate it would never see its success or failure. For the first time in history, progress would be measured not in human experience, but in abstract continuation. This creates a psychological barrier that is easy to underestimate. Human motivation is deeply tied to presence and legacy. We strive because we expect to witness results, or at least know that those results will matter within a familiar cultural framework. A project whose conclusion exists far beyond memory challenges the foundation of that motivation. It asks individuals and societies to care about outcomes detached from identity, language, and even species continuity as we currently understand it. Time also reshapes risk. On Earth, risk is evaluated against lifespan. A dangerous journey is acceptable if survival is plausible within one lifetime. Interstellar travel demands accepting risks that span generations. A flaw that goes unnoticed today may destroy a mission centuries later. A cultural shift could turn purpose into apathy. A technical compromise might become fatal only after the last engineer who understood it is gone. When cause and consequence are separated by centuries, accountability dissolves. Human biology compounds this problem. Our bodies are not designed for extreme longevity, nor for isolation across decades, let alone centuries. Even if medical technology could extend life significantly, psychological endurance remains uncertain. Long-duration isolation already challenges astronauts in low Earth orbit. Multiply that isolation by orders of magnitude and remove the possibility of return, and the strain becomes something entirely new. Space does not merely test survival, it tests meaning. The idea of altering human biology to adapt to interstellar timescales introduces ethical and existential dilemmas. Modifying lifespan, cognition, or perception to better suit cosmic distances may be technically imaginable in the distant future, but it raises a fundamental question. At what point does adaptation become transformation? A species capable of enduring millennia-long voyages may no longer be human in any recognizable sense. The cost of reaching the stars may be the surrender of the very traits that drive the desire to explore them. This tension reveals a deeper paradox. The universe invites exploration through curiosity, but demands detachment to complete it. To reach another star, humanity may need to think beyond individual lives, beyond cultural continuity, and beyond emotional reward. Yet those very things define what it means to be human. The qualities that push us to explore are the same qualities that make interstellar travel nearly impossible. Even perception itself becomes an obstacle. Humans experience time as a flowing present, anchored in memory and anticipation. Interstellar distances stretch that experience until it loses coherence. A journey lasting centuries cannot be imagined emotionally, only calculated intellectually. Without emotional grounding, commitment weakens. The mission becomes numbers, not narrative. And without narrative, civilizations struggle to sustain belief. This is why, despite technological advances, interstellar travel remains stalled at the conceptual level. The challenge is not simply to build machines that endure, but to build meaning that endures. A spacecraft can be engineered to last. A society must choose to care long enough to support it. That choice has no precedent on this scale. In confronting this reality, humanity is forced to re-evaluate what progress truly means. Perhaps advancement is not measured by how far we travel, but by how deeply we understand the limits we face. The stars may not be destinations in the traditional sense. They may be reference points, forcing us to confront the mismatch between cosmic time and human time. And in that confrontation, a quiet truth emerges. Before humanity can hope to cross the space between stars, it must first reconcile with the space between moments, generations, and meanings. Because the greatest journey may not be outward at all, but inward, toward a form of patience and continuity we have never had to master before. As humanity pushes against the limits of distance, energy, and time, a new kind of solution emerges, one that attempts to bypass the traditional rules of space travel rather than confront them head-on. Instead of carrying fuel, instead of accelerating massive spacecraft, these ideas focus on reducing the traveler itself. Shrink the ship, lighten the payload, and perhaps the universe becomes more negotiable. This line of thinking has given rise to some of the boldest and most unsettling concepts ever proposed, ideas that sound almost absurd until examined closely. One such idea is the laser-driven light sail. In this vision, a spacecraft would be no larger than a computer chip attached to an ultra-thin reflective sail. Rather than carrying fuel, it would be pushed forward by powerful lasers fired from Earth or from orbit. The light itself becomes the engine. In theory, this eliminates the tyranny of fuel and allows the craft to reach a significant fraction of the speed of light. At such speeds, a journey to Proxima Centauri could take decades instead of millennia. On paper, the idea is elegant. In reality, it is merciless. To accelerate even a gram-scale object to 20% of light speed would require an energy output comparable to that of a major power grid, sustained with extraordinary precision. The laser beam would need to remain perfectly focused across millions of kilometers of atmosphere and space, compensating for turbulence, orbital motion, and the rotation of Earth itself. A deviation smaller than a fraction of a degree could send the spacecraft drifting hopelessly into the void. Even if acceleration succeeds, another problem appears immediately: survival. At relativistic speeds, the environment becomes lethal. Interstellar dust, already dangerous, becomes catastrophic. A collision with a particle smaller than a grain of sand would release energy comparable to an explosion. A sail thin enough to be pushed by light would be shredded instantly. Protective shielding adds mass. Added mass reduces achievable speed. The solution undermines itself. Then comes the problem no one can elegantly solve: stopping. A light sail can be pushed forward, but once it reaches its target system, there is no easy way to slow it down. No fuel, no engine, no braking mechanism. The craft would pass through the target star system at extraordinary speed, collecting data for minutes or hours at most before vanishing into interstellar darkness forever. It would not arrive. It would pass by, briefly, like a whisper. This transforms the meaning of exploration. Instead of visiting another star, humanity would glance at it. Instead of arrival, there would be encounter without contact. Even the data returned would take years to reach Earth, delayed by the same distance that made the mission so difficult in the first place. Success would be partial, fragile, and delayed beyond immediate relevance. These realities force a sobering conclusion. Radical ideas do not eliminate trade-offs, they simply move them. By abandoning large ships, we abandon human presence. By gaining speed, we lose control. By avoiding fuel, we surrender the ability to stop. Each innovation closes one door while opening another, often darker one. This is not failure. It is revelation. The universe is not designed to be traversed easily by material beings. It resists shortcuts. It punishes impatience. Every attempt to cheat distance reveals a new layer of constraint, as if reality itself were enforcing a boundary between knowing and reaching. Yet these efforts persist, not because success is guaranteed, but because they redefine what is possible. A tiny probe that survives a flyby of another star would still mark a turning point in human history. It would be proof that the space between stars is not absolute, only costly. It would mean that humanity has begun, however tentatively, to extend its presence beyond the solar system, even if only as information. Still, something profound is lost in this transition. Exploration becomes impersonal. The human element, once central to discovery, fades into abstraction. No eyes witness the alien sky. No hands touch unfamiliar ground. What returns is data, stripped of experience, processed long after the moment has passed. This raises a final unease. If humanity reaches the stars only as machines, only as signals and measurements, does that fulfill the ancient dream of exploration, or does it transform it into something else entirely? The question lingers unanswered, suspended between ambition and acceptance, as the universe continues to remind us that speed and cleverness alone are not enough. As humanity reaches the edge of what technology can realistically attempt, a quieter and more unsettling realization begins to emerge. The universe is not merely difficult to traverse, it appears structured in a way that discourages physical expansion altogether. The more we learn, the more it seems that intelligence is allowed to observe far more than it is allowed to touch. We can see galaxies forming, stars dying, and planets circling distant suns, yet the space between them remains stubbornly resistant to occupation. This imbalance suggests that understanding, not movement, may be the dominant mode of existence on a cosmic scale. Every new discovery reinforces this pattern. Telescopes grow more powerful, data becomes richer, and our models of the universe more precise. At the same time, the practical limits of travel become clearer and more absolute. The cosmos opens intellectually while closing physically. It allows awareness without access, insight without arrival. This asymmetry forces humanity to confront the possibility that expansion was never the intended path of intelligent life, at least not in the way science fiction imagined. This does not imply meaninglessness. Instead, it reframes progress. For centuries, human advancement has been equated with outward movement, new lands, new resources, new frontiers. Space challenges that instinct. Beyond a certain point, expansion becomes less about conquest and more about comprehension. Knowledge flows more easily than matter. Light carries information effortlessly across the void, while mass struggles against every law that governs reality. The universe seems optimized for observation, not migration. This perspective casts Earth in a new light. Rather than a starting point to be abandoned, it may be a rare sanctuary where complexity can flourish long enough to ask questions about the cosmos. The conditions that allow intelligence to arise may also be the conditions that confine it. Stable stars, protective atmospheres, and long geological timescales are not just prerequisites for life, they may be anchors that bind it to place. The same stability that nurtures intelligence also limits its ability to roam. From this viewpoint, the stars become teachers rather than destinations. Each exoplanet discovered, each hostile environment revealed, strips away another layer of naive optimism. The universe does not appear hostile out of malice, but indifferent to convenience. It does not shape itself around life's ambitions. Life must adapt to its terms or remain where it is most likely to survive. This realization carries a subtle warning. If humanity views space as an escape from its own failures, it misunderstands both space and itself. There is no guaranteed refuge waiting beyond the solar system. The effort required to reach another star far exceeds the effort required to preserve the fragile equilibrium of the only world we know can sustain us. The universe does not offer second chances cheaply. At the same time, this understanding deepens the significance of exploration. The value of studying distant worlds is not diminished by our inability to reach them. On the contrary, it becomes more profound. Each measurement, each spectrum, each data point is a message from a reality vastly larger than human experience. Through observation, humanity participates in the universe without attempting to dominate it. This may be the most realistic form of cosmic presence available to us. Gradually, the dream of interstellar travel begins to transform. It becomes less about physical arrival and more about continuity of knowledge. Civilizations may rise and fall, but the light they collect and the understanding they pass on can persist. In this sense, telescopes, not starships, become humanity's true vehicles among the stars. They extend perception rather than bodies, curiosity rather than conquest. This shift does not diminish human ambition, it refines it. It suggests that progress may lie not in how far we go, but in how deeply we understand. The universe is not asking to be crossed. It is asking to be comprehended. And in learning this, humanity stands at a threshold more subtle than any physical frontier, a boundary between the desire to escape and the responsibility to endure. When Pluto and Proxima Centauri are placed side by side, they form a strange and revealing symmetry. One lies at the frozen edge of our solar system, a world still bound to the sun's gravity, faintly illuminated, reachable only with extreme effort and patience. The other exists beyond that boundary entirely, a separate star system, close enough to be named and studied, yet so distant that it may as well belong to another universe. Together, they define the outer limits of human reach, not just in space, but in comprehension. Pluto represents the furthest point where humanity can still send a physical presence, however brief and fragile. Proxima Centauri represents the point where presence dissolves into abstraction, where knowledge replaces touch and light replaces travel. From Pluto's surface, the sun would appear as nothing more than a bright star in a black sky, no longer a warming force but a distant reminder of origin. From Earth, Proxima Centauri is also just a point of light, indistinguishable to the naked eye from countless others, yet loaded with meaning because we know what it is. Both perspectives reveal the same truth. Distance erases familiarity. It strips environments of comfort and turns places into symbols. What once felt like home becomes remote, and what feels close becomes unreachable. Pluto taught humanity that even within its own solar system, time and distance impose harsh compromises. Reaching it required decades of planning and years of travel, only to allow a fleeting encounter. Proxima Centauri goes further, teaching that beyond a certain threshold, travel itself becomes optional, perhaps even irrelevant. We can measure, calculate, and observe without ever arriving. The universe allows us to know far more than it allows us to experience. This contrast exposes the limits of the narrative that has guided exploration for centuries. The idea that every horizon is meant to be crossed, that every boundary exists to be broken, begins to lose its certainty. Some boundaries do not yield to persistence alone. They demand transformation. To cross the gap to another star within a meaningful timescale would require changes so profound that they challenge the definition of humanity itself. Altered biology, radically different social structures, or forms of intelligence no longer bound to flesh may be required. The cost of reaching Proxima Centauri may not be technological, but existential. Seen this way, Pluto and Proxima Centauri are not failures of exploration. They are lessons. Pluto marks the point where engineering reaches its practical edge. Proxima marks the point where philosophy must take over. Together, they ask whether progress should always be measured in distance traveled, or whether understanding one's limits is itself a form of advancement. This reframing changes how we interpret the silence between stars. It is not an empty corridor waiting to be filled, but a vast filter allowing only certain kinds of interaction. Light passes freely. Information flows. Matter struggles. The universe appears to favor awareness over expansion, comprehension over occupation. Intelligence may not be meant to spread physically across the galaxy, but to arise in isolated pockets, each one observing the whole from its own fragile island of stability. This possibility carries a sobering implication. If intelligent life elsewhere faces the same constraints, then the galaxy may be full of watchers rather than travelers. Civilizations may detect one another across light years, exchange indirect signals, and infer each other's existence, yet never meet. Contact becomes asymptotic, always approaching, never arriving. The famous question of whether we are alone takes on a different tone. We may not be alone, but separated by barriers that make solitude functionally inevitable. In this context, the fascination with Proxima Centauri is no longer about reaching it. It is about what it represents. It is the nearest proof that other suns exist, that other planetary systems form, and that the universe repeats its structures beyond our own neighborhood. It reassures us that Earth is not unique in form, even if it may be rare in outcome. At the same time, It reminds us that proximity does not equal accessibility. Pluto and Proxima Centauri stand as two opposing mirrors. One reflects the limits of our machines. The other reflects the limits of our nature. Between them lies the full weight of human ambition, stretched across a scale it was never designed to inhabit. And in recognizing this, humanity is forced to confront a final question, not about distance or technology, but about meaning. If the stars are not meant to be reached, then what are they for? The answer does not lie in propulsion or power, but in perspective. The final lesson of these distant worlds is not about how far we can go, but about how we choose to live with the knowledge that there are places forever beyond our grasp. And that realization prepares us for the last part of this journey, where the limits revealed by space turn inward, asking what it truly means for humanity to stand where it does in the vastness of the universe. At the end of this long chain of questions, calculations, and realizations, a quiet conclusion settles in. Pluto and Proxima Centauri are not merely distant objects in space, they are symbols of a deeper boundary that humanity has only recently begun to recognize. They reveal that the universe is not structured around human ambition, speed, or desire. It operates on scales where patience outweighs power, where endurance matters more than ingenuity, and where understanding often comes long before access. The farther we look, the clearer it becomes that the cosmos does not invite conquest. It invites awareness. Human history has been shaped by the belief that limits exist to be overcome. Mountains were crossed, oceans were sailed, continents were mapped. Each time, the horizon moved farther away, reinforcing the idea that progress is a continuous outward expansion. Space breaks that pattern. It introduces limits that do not yield to persistence alone. The speed of light is not a challenge to be engineered around. It is a boundary woven into reality itself. Time, energy, and distance do not negotiate. They simply are. This realization does not diminish humanity. It refines it. For the first time, intelligence must confront a frontier that cannot be rushed, conquered, or claimed. A frontier that forces reflection rather than expansion. Pluto reminds us that even our own cosmic backyard is vast and unforgiving. Proxima Centauri reminds us that the stars, though visible and measurable, may remain forever beyond physical reach. Together, they teach a humbling lesson: knowing is easier than arriving, and perhaps more important. In this light, science takes on a different role. It is no longer only a tool for mastery, but a method for humility. Each telescope, each probe, each equation extends our perception without promising control. The universe allows us to witness its grandeur while denying us ownership. And that denial may be essential. A species that could move freely between stars might never learn restraint. A species confined by distance is forced to value what it already has. This reframing shifts the meaning of the search for life beyond Earth. It is not an escape plan, nor a promise of new homes waiting to be claimed. It is a mirror. By studying distant worlds, we learn what makes our own world fragile and rare. By imagining interstellar journeys, we confront the limits of our biology, our societies, and our patience. The stars do not offer easy futures. They offer perspective. Perhaps the most profound outcome of space exploration is not expansion, but responsibility. When the universe makes clear how difficult it is to leave, it also makes clear how vital it is to preserve what allows us to exist in the first place. Earth is not merely the starting point of a journey outward. It may be the most extraordinary destination we will ever know. Its stability, its protection, and its capacity for life are not guaranteed elsewhere, no matter how many planets we discover. This does not mean the dream of reaching the stars will fade. It will evolve. Humanity may send machines where bodies cannot go. It may exchange information rather than presence. It may measure success not by arrival, but by continuity of knowledge. In doing so, exploration becomes quieter, slower, and deeper. A conversation with the universe rather than an attempt to cross it. In the end, Pluto and Proxima Centauri stand not as failures of ambition, but as guides. They mark the boundary where curiosity matures into wisdom. They remind us that intelligence is not defined by how far it can travel, but by how well it understands its place. The stars remain distant, cold, and silent, Yet they continue to shape human thought in ways no spacecraft ever could. And perhaps that is the final truth hidden in the vastness of space. The universe does not exist to be conquered by humanity. It exists to challenge it, to humble it, and to expand its awareness. Standing beneath the night sky, knowing how far and how unreachable those distant lights truly are, we learn something rare and essential. That meaning does not always lie beyond the horizon. Sometimes, it lies in recognizing why the horizon exists at all.